Hello everyone, my name is Peter Huang. I'm going to talk about the intensification of biofuel process integrating membrane solvent extraction with fermentation and distillation. My topic includes introduction, modeling of intensified MSE integrated biorefinery, and conclusions. First, let me give some introductions. Bioethanol is one of major renewable biofuels. As shown in the chart, the US currently has around 210 ethanol plants with total ethanol production of 16 billion gallons per year. It is important to explore the improvement and intensification technologies that can reduce the energy consumption and the environmental impact and increase the profit. There are two types of ethanol processes, the wet mill and the dry mill ethanol process. There are several challenges for ethanol production: high feedstock cost, product ethanol inhibition, high energy consumption resulting in high separation and purification costs, and a large amount of water usage. To reduce energy consumption and production cost, to reduce water usage and accelerate fermentation for increasing productivity, the modeling work here is aimed at ethanol process intensification by integrating membrane solvent extraction with fermentation and distillation. Now let's focus on modeling of intensified membrane solvent extraction integrated ethanol biorefineries. Here is the diagram of conventional distillation in the ethanol process. The broth from beer well, after removal of carbon dioxide, enters the beer column. The resulting top vapor containing 42% ethanol. This vapor then enters the rectifier to get 91% ethanol. The bottom slurry of the beer column is separated into liquid water and solid DDS. This is the intensified ethanol process with MSE integration. The red blocks in the middle represent the integration of MSE and distillation. After the solids and carbon dioxide are removed, the clean broth enters the first module of the MSE system, and at the same time, the solvent or extractant enters the last module in a countercurrent flow. The ternary from MSE after flashed enter the solvent column to recover the solvent for reuse in MSE. The distillate from the solvent column then enters the rectifier to get 91% ethanol. This is a schematic of the MSE integrated process used in DOE studies. In the process, the feed starch enters the fermentation to be converted to glucose, then glucose to ethanol. The resulting broth, containing 10% ethanol, then enters the first one of the 9 membrane modules in series. At the same time, the extractant enters the last membrane module in a countercurrent flow. The thin broth from MSE after removal of crossover extractant by gravity and re-extraction with dodecane is recycled to fermentation. The ternary from MSE enters the solvent column to strip off the extractant for reuse in MSE. Now let's compare the MSE distillation integration and the conventional distillation. Here is a simple conventional distillation process without including fermentation, carbon dioxide absorption, and recycling streams. In this process, the broth enters the beer column for pre-concentrating ethanol. The resulting vapor, containing 42 to 50% ethanol, then enters the rectifier for further ethanol concentration. And lastly, the resulting distillate, containing about 91% ethanol, is dehydrated with molecular sieve. Here is the MSE distillation integration. In this simple process, the tunnel from MSE enters the solvent column for pre-concentrating ethanol and recovering solvent for reuse. The resulting vapor contains 72 to 84% ethanol. This vapor then enters the rectifier for further ethanol concentration. And lastly, the resulting distillate, which contains about 91% ethanol, is dehydrated with molecular sieve. In the process modeling, plant size is fixed at 100 million gallon ethanol per year, assuming 8,410 operating hours per year. Here are the parameters used in the process modeling. 2 distillation columns of conventional process operates in pressure slightly higher than atmosphere, and 2 distillation columns of MSE integrated process operate in vacuum conditions. The table here shows the energy data from the process simulation. For the conventional distillation, the heating and cooling energy of the 2 distillation columns increase with decreasing ethanol concentration in the broth. This is because at the lower concentration of ethanol, higher reflux ratio is required to get the same product concentration. Currently, cellulosic ethanol processes can only produce about 5.5% ethanol. This is not economic to distill in the conventional process. With MSE, it becomes economic to distill. As shown in the table, distillation of ethanol from ternary requires significantly lower heating and cooling energy, especially for the broth containing 8% or less ethanol. Here. Now let's compare the MSE integrated process with the conventional distillation process. Both are closed systems. Look at this conventional distillation process first. It includes glucose fermentation, carbon dioxide scrubbers, and all necessary recycling streams. For example, this stream is recycling, and this stream recycling, and this stream are also recycling for use. Except the required input feed materials such as glucose and water, and the outlet streams such as vane gas and the product ethanol, all other streams are recycled. So, it is relatively a closed system. Now let's look at the intensified integrated MSE distillation process. The differences between this and the conventional process lie in the added MSE and the operating conditions of the two distillation columns. With the MSE added and integrated, the separation process changes from ethanol water separation to ethanol DMHT water ternary separation. Accordingly, the operating conditions of the two distillation columns are different between the two processes. Specifically, the solvent column is operated under vacuum condition to pre-concentrate to 72 to 84% ethanol and recover the extractant for recycling use. In contrast, the beer column in the conventional distillation process in the previous slide is used to pre-concentrate to 40 to 50% ethanol, which is more diluted than here. Here are the parameter values used in the process modeling. Here are the energy data from simulation. For the conventional distillation, the heating and cooling energy increase with the decreasing ethanol percent. For the MSE process, the heating energy consumption for different ethanol concentration here and here are almost the same, assuming the same ternary composition. Therefore, the lower ethanol percent in the broth, the more energy saving for MSE integrated process compared to the conventional process. The MSE integrated process requires 25 to 35% less heating energy and 15 to 35% less cooling energy for the broth of 5 to 10% ethanol. The case of broth containing 8% ethanol and assuming the ternary composition here, the heating and cooling energy of the MSE integrated process still much lower than the conventional process, and this is represent the fermentation acceleration mode. This is the fermentation acceleration mode with integrated MSE for process intensification. The thin broth containing 1 to 2% ethanol from MSE is recycled to fermentation to control ethanol concentration of the broth at 8% ethanol. At 8% ethanol or below, the product inhibition is eliminated, leading to increase in productivity. It is seen from the DOE report that this could increase 2 to 3 times acceleration. As shown in the previous slide, the heating and cooling energy could be substantially saved. In summary, simulation shows that membrane solvent extraction could substantially reduce the heating energy requirement. MSE could have substantial water savings and improve the environmental impact. The integration of MSE allows eliminating product inhibition, accelerating fermentation, and increasing the productivity. The integration of MSE with fermentation and distillation could be more efficient with potential reductions in overall production cost. Our future work will be on process modeling and techno-economic analysis of the intensified cellulosic biorefinery with integration of MSE. Thank you for watching.